So this is work that we developed together with James Noble, Susan Eisenbach, and Julian Mackay, and it started some years ago when I was observing James and Mark Miller discuss about object capabilities. As a little bit of background, Mark Miller proposed object capabilities for securities in his thesis. I think it was 2006 or something, and this really caught on. And then he was invited to participate in the design of ECMAScript for a robust version of JavaScript, and where they removed various bad bits like ambient authority, like static fields, and added further features that should allow for better security, like, for instance, membranes. So James was discussing with Mark about what good encapsulation features should be added to JavaScript or to the next JavaScript, to the ideal programming language. And so Mark was discussing this, and James, of course, was proposing some version of ownership types. And then I asked, but what do you want to ensure with those encapsulation features? And we came to the conclusion that things like private fields or ownership types or membranes, and there are all mechanisms that allow you to write secure programs, but how are these mechanisms used? So this is the subject of the discussion today, and I'm going to give you the background that we are working with, the problem, then what do object capabilities do, and what is our remit. So the background is that we have got internal trusted objects, and they collaborate with external unknown objects of unknown provenance that are untrusted. They may be benign, but they might be malicious, whatever, but we don't know about them. So there's a tight intertwining between those two. And now the external objects call into the internal objects call into the external objects. And the problem is there is a lot of uncertainty. How do we mitigate this uncertainty? The solution proposed by object capabilities is that the capability is a particular object, and if you have access to that capability, then you can have some effect. You can run an operation and change the world. If you don't have access to that capability, then you cannot run this particular operation. And therefore, it's very important that we control how the capabilities are passed around, so you cannot forge the capability, and the only way that you can get the capability is if somebody gives it to you. Now, so far, this is what the capability literature is saying. Our remit was to put it to a formal footing to explain those guarantees and to prove that those guarantees are indeed given. So we want to specify indeed the role of the capability. We want to prove that the module satisfies the specification. We want also to deal with external calls. We want to be able to reason about what happens if I have an internal object, it calls into the external world. The external world is unknown. How do I know that it does not come and mess with my stuff? And what is not our remit is to limit how much the external world knows about the internal world, whether it has got access. So we are not a type system. We don't put a fence around our capabilities or the internal objects. We just say they collaborate, and they collaborate robustly depending on the on the graph of objects and the shapes of those objects. So first of all, the background in a diagram. We have got the internal trusted objects, they are green, and the external, they are red. So here is the standard example in, at least in object-oriented programming, where we have got an account and it has got a password, a balance, and there is a shop that has got the account to keep its money. And there are some external objects, and they have got references to the internal objects, and the internal objects have also got references to the external objects. So the external objects may call method on the internal one. So here is 6 calling a method on 2, 5 calling a method on 2. The internal objects may call methods on the external one. So here is the shop calling a method on 5. And the solution, as I said earlier, is to use to this uncertainty that comes from that intertwining, is to use object capability, and the capability is this transferable right to perform an operation. But I want to make it a bit stronger, what is said. So now I'm using our terminology rather than OCAP terminology, where the capability is not just something that enables an operation. A capability is a necessary condition for an effect. So the capability is the guard for this effect. The capability, for instance, having access to the password is necessary in order to take money out of the account. If you do not have the password, you don't take money from the account. So the first remit is to specify this, and what we would say is without eventual access to an account, you cannot modify the balance of the account. The second specification is without eventual access to the password, you cannot remove money from the account, you cannot reduce the balance. So they're slightly different, and therefore 5, but calling into 2, it can pay into 2, so it can increase the balance, but it cannot reduce the balance of 2. On the other hand, 6 has got eventual access to the password because it can go through 7 and get to the password, so it may reduce the balance. The next remit is to prove indeed that the module is the code of those green objects, that it satisfies the specification. I'm going to talk about this later. And the next remit is to prove when we go from internal objects to external objects. So here is the shop, it's calling into an unknown object. And we have got the guarantee that without access to the password, we cannot decrease the balance. So if a shop calls into this unknown object, and if it knows that this unknown object does not have access to the password, then it can be sure that the balance is not going to be decreased. So it's a kind of safe call. On the other hand, if it calls into 6, which has got the eventual access, then such a guarantee is not given. And what is not our remit again is we do not try to restrict how the external objects have access to the internal objects or to the capabilities. In particular, it doesn't make sense to say nobody external has got access to the password, because if nobody external had access to the password, then the account would not be usable to anybody. We want to give the accounts to some people, and they should be able to make their payments with the accounts, but we want to have the certainty that those who do not have access to the password will not take the money out of it. So I'm going to revisit the example now in code. And here is a first version of a very simple module where I have got passwords in the accounts and the method that transfers money and first checks that the password given is the correct password, and the method that allows me to set the password if the password was null. And then I have got another version of the module, and this is a bad version of the module. I have modified the method set so that I can reset the password to whatever I want. And the third version of the module, the find module, which has got a method set, but does not modify the password unless you already gave it the correct password. So here is our diagram again. And what we would like is a specification language that would allow us to distinguish between the good modules, the good and the fine, and the bad one. Secondly, I want to be able to prove that indeed the first and the third module satisfy that specification, and the second one doesn't. And thirdly, I want to deal with external calls. So let's have a look at this method, this class shop, which has got a method buy. There is an external buyer, and he wants to buy a certain item. So what do? We calculate the price of the item that he wants to get. We calculate the current balance, and then we ask the buyer to send the money. So we tell the buyer, pay me into my account this price. And then we continue, we check whether he has paid. If he has paid, we send the item and so on. But here we have got an external call, the open call. Here we are calling into the unknown world. So at this point, all bets are off. However, if we are in this situation, if we are in the situation where the buyer doesn't have the access to the password, then we know that provided that our account here comes from a good module, our account is robust, and provided that the buyer has no unprotected access to the password, so doesn't have access to 2, then the balance will not decrease afterwards. And we would like to be able to prove that. So that is the third remit. Develop the rules that would allow us to prove that. So first, I'm going to discuss the specification language, and we go back to the capabilities, transferable right, and what it allows us is to get some effect. So the first attempt would be to say the password enables withdrawal from the account. So if you have the password, you can withdraw. However, that's not good, because this is talking about a sufficient condition. It says if you have the password, you can do. But we want to be able to say the opposite. If you don't, then you cannot do. So we go for, without the password, the call to withdraw will fail. But we want to go further and say without eventual access. So if you don't have a means of getting the password, so this is the first generalization. And also, I don't care whether I call withdraw or transfer or whatever function, I care for the effect. So the reduction of the balance will not happen. So this is the way we specify it, and we specify it with an invariant, essentially. We say that for all accounts and for all numbers, if I am in a state where there is no way for anybody external eventually to get access to the password, then the balance is going to be greater, equal a certain number. So this comes from the two-state invariants that were proposed already actually by Barbara Liskov and Janet Wing, but it has got some different flavors, and I'm going to discuss this a little bit later on. Right, so in general, our specification have got this format with a couple of universally quantified variables and then an assertion. And we need to clarify two things. First, what does it mean, or how do we write without eventual external access? And the second, what is exactly the meaning of this two-state invariant? Here is the specification for this particular property. So, what is this without eventual external access? How much time do I have? 10 minutes. Okay, right. Okay, so without eventual external access is described through in two steps. In two steps. We first define what does it mean for an object to be protected from another object. And the object is protected from another object if the penultimate object, if I take any path from O prime to O, then the penultimate object must be internal. So if I take here any path from 5 to 1, then I must go through an internal object. So 1 is protected from 5, but it's not protected from 6 because I can go 6, 7, 1. And similarly, 2 is not protected from 4 because I can go 4, 5, 2, and 2 is not protected from 8. So the protection is a relative property, is relative to another object, and in general, lots of things are relative properties. If we consider our example from earlier, I can now give a specification that says, if the password of my account is protected from the buyer, then I know that afterwards the balance is going to be decreased. And now we get to what it means for an object to be protected, and the object is protected if in the current top of the stack, in the currently accessible objects, like here, in the current top frame, none of the external objects that are reachable from the top frame have unprotected access. So in this frame, 1 is not protected because I can go in an unprotected way from 7. However, if I push more frames, like here, I have got one more call, now 1 does become protected. And 2 was not protected, but if I push one more, then it is protected. So we have got to this concept of protection. This is relative. The next question is, what do these two-state invariants mean? And some of the definition is, it goes along the general idea of two-state invariant. So we start with a state that is external because we are only interested in preserving the invariants from the point of view of the external world. And in that state, we find a couple of objects that are from the classes as required here. And we say in that state, the assertion holds, but we have to do some replacement of the variables by addresses just for technical reasons. Then we do any number of steps, and then we know in the new state, sigma prime, if we are in an external world, then the assertion still holds. The only interesting thing, a little bit unexpected, is that we think about external states, and we have what we call scoped execution. I'm going to discuss it in what that means. So the scope execution is a normal execution, but we only look at things that are in the future from my point of view. So let's consider this example where I have got an internal state that makes a call into an external method. So an external state, some more calls. If I go up, I make more calls. Then I start returning, and so on and so on. This is just calls happening, and when I go up, and returning from calls when I go down. So if I look at the scoped execution, I want to only look at things that happen while I'm not popping the top frame. So if I start at sigma 4, I can get to sigma 18 without popping the top frame of sigma 4. I did pop some frames here, but I didn't pop the frame of sigma 4. So this is in the scope execution. Similarly, from sigma 4 to sigma 20, we did pop frames, but not our. So this is in the scoped execution, but sigma 4 to sigma 21 is not scoped, and sigma 4 to sigma 24 from here to there is not scoped. So this guarantee means that if I go from sigma 4 to sigma 18 or to sigma 20, I preserve the property, but not otherwise. So again, we have got a concept where something is scoped by another state. And now I can give the 4 specifications of my module that if an account is protected, then it remains protected forever. If a password is protected, then it remains protected forever. If the account is protected, then the balance doesn't change. If the password is protected, then the balance only increases. So we see that my specification is API agnostic. Whether I do the transfer through the method transfer or pay or whatever, doesn't matter. It's also agnostic about the internal representation in the module. I could have implemented the module through a ledger where I kept a mapping from accounts to their passwords and their balances or whatever other methods. And we are talking about the emergent behavior. So the behavior that comes through execution of several methods. So the bad module doesn't satisfy sigma 2 and doesn't satisfy, specification 2 nor specification 4 because of its emergent behavior, because you can call the method to set the password and then take out the money and then you break S4. So you have to think about all the methods together when you are making such specification, and the other one, the other modules satisfy them all. So second challenge, an inference system, which allows me to make those proofs. First of all, I need the concept of what does it mean for an assertion to be encapsulated, and an encapsulated assertion is one that can only be broken by calls into the module itself. I need a whole logic, and we go into 3 stages. In the first stage, we assume that there is an underlying whole logic that does stuff for us. It does not know anything about protected and so on. This is our remit, but it does the basic things. Then from this, we go into a whole logic of triples with standard meaning. Then we expand it to quadruples. So this part is the standard meaning, but we also make the guarantee that if I call into an external method, then I'm going to only call if the third assertion holds. And then we can prove that the module satisfies the specification. So I'm going to skip things a little bit. So how do I prove that the module satisfies the specification? It has to, that the module is well formed, it has to satisfy the specification, standard rule for combining various specifications. And now how do I prove that those invariants are upheld? So what we have to do is first we need to know that this invariant is encapsulated, because otherwise it's, anybody can break it. Then we have to find all the public methods in the particular module, and then we have to prove that those public methods preserve the invariant. I have to do a little bit of work here to make the pre-form of the assertion and here the post-form. I'm not going to discuss this because I want to get to the last part of the remit, which is the external call. So here I am calling a function on y0, and I know that Y0 is external. So I have no specification. I have got no guarantee that what this method might modify. I cannot use separation logic. I cannot say this part of the state is all mine. He's not going to touch this part of the state. So, but what I do know is that the module is making some promise. So the module says this assertion A is going to be preserved by the external calls. So I should be able to use it here. In order to use it, I need to know, first of all, these X's indeed belong to those classes. And I need to be able to also say the assertion A holds. But I will do a little bit of a modification on the A. So it is A with this adaptation from the point of those Y's. I'm going to explain it. And then I know this A holds after the call. And I also know that during the call, any call to an external function will preserve the A. So now what is this mysterious adaptation operator? It is something that changes the assertion from the point of view of the caller to the point of view of the callee. So let's look at this situation, 4 calls into 5. And we have this general guarantee that if the password is encapsulated, then the balance is not going to be modified. From the point of view of 4, the password, which is 1, if the password is protected. So from the point of view of 4, the password is not protected. But from the point of view of 5, it will be protected. So this operator allows me to obtain this certainty that even though something might not hold here, it will hold when we push the thing onto the frame. And we said that protection is relative to a frame. So there is this operator that allows me to guarantee that if something will hold when I push a frame. So here is the corresponding lemma that says if A with this viewpoint adaptation from the Y's holds, then if I have pushed the Y's onto the top frame of the state, then A is going to hold. And this is the magic. So protection is relative, and we have got this operator, and I'm not going to go through that because I have overrun. Thank you very much.
We're running a little bit behind schedule, but maybe there's time for one question, if anyone has very questions. You sort of got through external and internal, but I wonder. But I wonder. Okay, sorry, wasting time here. But I wonder if this could sort of be extended to some kind of lattice or something like that.
The current thinking should be that there should be various externals, and we should have some guarantees about whether they talk with each other. So we are not a data flow. We're not inspired by flow security, but we are just thinking about those externals. Currently, all the externals are like a blob. They can talk to each other and pass everything to one another. But I think realistically, they are islands, and unless something introduce them to each other, they will be separated.
Great. Okay, thank you. Let's thank Sophia once again.
Thank you.